Hey everybody, this video lesson is going to cover the quantum mechanical model and quantum numbers. Now, the quantum mechanical model represents regions of electron probability and not electron orbits. Bohr's model had electrons traveling in predictable orbits, but Heisenberg and Schrödinger's contributions to the quantum mechanical model resulted in a new model that represents electrons floating around in space in random spots. Now, the quantum mechanical model is organized from broad to more specific. So you first identify the energy level, and a broad energy level is basically a region of space around the nucleus. Now, this is a holdover from Bohr's model. Bohr came up with the idea of energy levels. So the quantum mechanical model uses the idea of energy levels, but it says within those energy levels, as you get further from the nucleus, there's more space for electrons to spread out and occupy these things called subshells. Now, a subshell is identified as an S subshell, P, D, or F, and these become more complex as you work from left to right. S subshell, which we will talk about later, only is made up of one orbital, where a P subshell is made up of 3 orbitals, and a D 5 orbitals, and an F 7, and so you get more complex or more pieces, more orbitals in the subshells as you move out. You don't have an F orbital uptight close to the nucleus. It's not till you get a little bit further out from the nucleus where you start to see the F orbitals show up. So not all energy levels contain all these orbitals. Finally, the electrons fit into the orbitals, which make up the subshells, which are pieces of the energy level. So as you see, we're getting more specific going down. Remember, an orbital's basic definition is that it is an area of an electron probability, or in other words, it's a spot where electrons live. An orbital itself doesn't really exist. It is more of just an area of space around the nucleus. And so you can only really know what they look like by hypothesizing using multivariable calculus. Have you ever messed around with those multivariable graph calculators on the internet? Maybe you even have one on your own calculator. They're pretty cool. You type in some random letters and numbers and variables, and you hit graph, and it generates these strange three-dimensional figures. Well, that's what these orbitals really are three-dimensional figures using multivariable calculus. I like to think of electron orbitals as three-dimensional electron density maps. Now, I'm a big soccer fan, and usually in the soccer analysis, you can isolate a particular player and look at it, their heat map, for example, where they're touching the ball on the field most often, which gives you an idea of where the player plays most of the time. For example, if they're an outside midfielder, they will typically stick to the side of the field, and they could be a left-sided midfielder or a right-sided midfielder. But the midfielder's heat map would show their travel, the path they travel, only on one side of the field. And that's kind of what an orbital does, is show an electron's path of travel, or where it's most likely to be found. That doesn't mean that the electron can't travel outside of its orbital. In fact, there's a probability that it does. There's a calculated probability that it does. In fact, that probability is 10%. But a 90% chance that the electron is found within the orbital. And that's what an orbital is. It's a area of electron probability. Just like a player who plays on the right side of the midfield in a soccer game, nothing says that it can't travel across the field and find itself on the left side of the field. The player is the electron. It generally finds itself on the right side most of the time, but sometimes, 1 in 10, it will find itself on the left side of the field. If you're familiar with hockey, the goalie almost always finds itself standing in front of the net, but that doesn't mean the goalie can't go outside the net and maybe gather the puck behind the net. But generally speaking, the goalie only stands in front of the net. So in other words, sports analogies make a good representation of how electrons travel in these orbitals. So let's take a look at this picture here on the right. This right here is a graphical representation, and it's only in 2 dimensions, but imagine it's 3-dimensional and it's coming out at you. But this is what a 1s orbital looks like. And up close to the nucleus, you can see it's much darker red or darker pink. Down here on this graph, you can see probability versus distance from the nucleus. And when you're close to the nucleus, there's a high probability of the electron being located there. And as you move further from the nucleus, you can see that the probability decreases till it's essentially zero. And that's what it's showing here, that as you move further from the nucleus, the color gets lighter and lighter and lighter. And eventually, once you get way out here, the probability is incredibly low of the electron occupying the space out here. And that's what an orbital is trying to represent. This is two different ways to represent. This is the heat map, and this is the graphical representation. If you took an orbital and then put a 2s orbital over the outside of it, like this second picture, this 1s orbital is up tight to the nucleus. Well, this 2s orbital actually covers the 1s, it envelops it. And if you were to slice it down the middle, what you would see is the 1s in the middle and the 2s orbital on the outside. And you'll actually notice this region of empty space. It's called a node. And basically, it's the empty space between two orbitals. Now, a 3s orbital will go outside the 2s, and that would then have two nodes. So the third s energy level is larger, but it's still an s orbital because it still has the same shape. And this is what it will look like if you cut it down the middle in a cross section, almost like cutting an onion down the middle. You can see the layers. Now, this is what the orbitals would look like if you didn't cut them down the middle. They would have basically increasing size spheres. But as you know, inside the 3s is the 1s and the 2s. Now, starting in the second energy level, we have more room for more electrons, and those more electrons can occupy a different type of subshell. And that subshell is called a p orbital. Now, a p orbital is just one of these, but combine them together and you have the p subshell. And this is the 2p orbitals. There are three of them. And they're orientated on the XYZ planes on a three-dimensional graph. So the first one has two lobes and it's on the x-axis. The second one is got two lobes and they're on the y. And the third is got two lobes on the vertical z-axis. Now, if you were to take those and put them all together, they would all combine together in the middle. And so what you get is one p orbital going horizontal, one p orbital going vertical, and one coming out at you, and the other one kind of going back into the board. And as you can see by my beautiful art drawing skills, that this p orbital is clearly made up of three different p orbitals. This is a p subshell made up of three p orbitals. Now, we mentioned as you get a lot further along on the subshells, they get more complex, and a d subshell is split up into 5 orbitals. Now, this just represents 3 different pictures of the 5 orbitals that make up the d subshell, but these are what they look like once again graphed on the XYZ three-dimensional coordinate plane. You've got a set of lobes here, 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 and here, and you fit them all together and you get the d subshell. Now, this doesn't begin to show up until the third energy level because we can't fit that many electrons around the nucleus until we get a little bit further from the nucleus. So the third energy level is where we see the emergence of the d subshell and the 5 d orbitals that make up the d subshell. Finally, the most complex of these subshells is the f subshell, which is made up of 7 orbitals. And as you can see, this doesn't begin until you get to the 4th energy level. So the 7, as you can count them, orbitals make up the f subshell. And if they all combine together at the origin of the graph, so you put this and superimpose it onto this, and superimpose it onto this, and superimpose it onto this, and superimpose these 3, all you get is a jumbled mess of orbitals that make up the f subshell. But know that these orbitals are actually mathematically determined, and they are regions of electron probability. But truly, if you shoved them all together into one spot, it would just kind of look like a sphere. But don't be confused with what it looks like with what it actually does, because the fact that these electrons live on different orbitals and different subshells means that these electrons behave differently. An f orbital behaves differently than a d orbital electron behaves differently than a p orbital electron. And so these orbitals actually are evidence to support our concepts of bonding and our concepts of molecular shape. So these models of the atom with their different orbitals support theories that we accept as truths in chemistry. Remember, just because it's a theory doesn't mean it's not true. Theories are truths that are accepted and supported by data in chemistry and in science. And these theories, along with other theories such as bonding theory, support one another and give us a more full picture of what an atom looks like and how it truly behaves by itself and when it participates in chemical reactions. Now I'm going to introduce to you the concept known as quantum numbers. It's a notation that represents a specific electron as it lives or as it travels around the nucleus of a specific element. So it's a way for us as chemists to take a look at individual electrons, because no two electrons have the same set of quantum numbers. No two electrons are identical. No two electrons are in the same place at the same time. So no two electrons can have the same set of quantum numbers. And it helps us identify where the electron is around the nucleus, how far it's away from the nucleus, which subshell it's in, which orbital it's in, and which direction it's traveling. Now the first quantum number is the most basic quantum number. It's called the principal quantum number, and we call that quantum number n. Now n is equal to the size of the energy level. So if the electron is in the first energy level, then n equals 1. If the electron's in the second energy level, then n equals 2. Now getting a little bit more specific, we use the next quantum number. We call it the angular momentum quantum number, or just L. Now usually it's written as a cursive L. As you can see, it's kind of italicized here, but that's difficult to identify. Is it liquid? Is it the number 1? So usually we use the cursive L to represent the angular momentum quantum number. Now the angular momentum quantum number tells you which subshell it's in. And these are going to be represented by the numbers 0, 1, 2, or 3. So if it's 0, then it's in a S subshell. If it's a 1, then it's in a P subshell. If it's a 2, it's in a D. And if it's a 3, it's in an F. So if I say that the energy level is 2 and the L value is 1, well, we know it's in the second energy level, P subshell. The third quantum number gets a little bit more specific yet. This is called the magnetic quantum number, or M subscript L. And so this tells you which of the orbitals of the subshell that an electron is in. Now remember, an S subshell only has one orbital, and so we only have one option for the M subscript L, or M sub L number. The P subshell has 3 orbitals, and we need to identify which of those orbitals the electron is in, because some are in one of the orbitals, but they're not all in the same orbital. And so we need a way to identify that using numbers. And the way we do that is we use symmetrical whole numbers, positive and negative, around 0. Now the S subshell only has one orbital, so we just use 0 for S. But P has a possible 3 orbitals, and we identify them as -1, 0, and 1. And as you would imagine, the D subshell has 5 orbitals, so they're symmetrical and around 0. So we can go 0, +1, and +2, and also -1 and -2. And that's how you get the M subscript L values for the D subshell. And the F then would have ±3, 2, 1, and 0, which would make up its 7. So here's a table breakdown of the possible values and the possible subshell designations and the possible orbital designations for different electrons as they exist around nuclei. And so as you look over here on the left, we've got it broken down into higher energy levels going down. And the first energy level, you can only have an S subshell, which we identify the S as 0. This is the designation as quantum number. This is what we call it. We call it the 1s orbital. The possible values for that, since there's only one orbital in that subshell, then it's a 0. Starting in the second energy level, we have the S and the P. Now of the P subshell, there are 3 possible values for the orbitals, ±1 and 0. 3. They just aggregated these right here. Now, total number of orbitals in that shell is 4. There's an S and 3 P orbitals, or 4 total. Now the third energy level, we've got 3 possible values for L, because we're expanding, we're getting more space around the nucleus, so now we can add a d orbital, which we identify as L equals 2. Now that d orbital has its own ±2, ±1, and 0. So there's 5 there. There's 3 from the p orbital in the third energy level and 1 from the s orbital. So add these up and you get 9. So you can see an exponential growth. You go 1 to 4 to 9 to 16. Finally, in the fourth energy level, you now have 4 subshells. which we identify as 4s, 4p, 4d, 4f, the values of L assigned to each one are 0, 1, 2, and 3, and thus we have the built-out pattern that emerges. We now have plus or minus 3, 2, 1, and 0, 7, add these up, and you get 16. So this table helps us summarize the different possible values and the relationships between the energy level, the subshell, and the possible m sub L values. And finally, only 2 electrons can fit in any orbital. So we designate each electron in an orbital as either an up arrow or a down arrow. If you only have 1 electron in an orbital, it is either an up arrow or a down arrow. But if you have 2 electrons in a particular orbital, they have to be opposite, one up and one down. In order to represent an up-spinning electron or a down-spinning electron, we use one final quantum number, and it's the ms number, or the spin number. And that can only be either plus 1/2 or negative 1/2. Don't ask me why it's not plus 1 or minus 1, why it's only a half, but it is. It's only a half. So we either have plus 1/2 or minus 1/2. So an up arrow only would represent plus 1/2, and a down arrow would represent a negative 1/2. So now you might be asking yourself, how do we put this into practice? What sort of questions could you be asked that pertain to quantum numbers on an upcoming quiz or test? We'll take a look at this one. It says, for a principal quantum number n equals 3, determine the number of allowed subshells or different L values of the given and the given designation for each. When I say given designation, I mean 1s or 2s or whatever. So remember, in the third energy level, when n equals 3, there are 3 possible L values. That pattern emerges. In the first energy level, there's only 1 possible L value. In the second energy level, there's 2 possible L values. In the third energy level, there's 3 possible L values. Now remember, as we learned on the last slide or the last couple slides, the possible values for L are 0 for S, 1 for P, and 2 for D. So the designations, this is the 3S, this is the 3P, and this is the 3D. And you've got yourself the answer to this question. We've identified the allowed subshells, 0, 1, and 2. There's 3 possible subshells, and the different values or the designations for each are 3S, 3P, and 3D. Here's another example of a question you might see on an upcoming quiz or test. Take a look at the set of 4 quantum numbers that you see in this table. There's 4 sets, 1, 2, 3, 4. I've identified them as set 1, 2, 3, or 4. Now set 1 identifies these set of quantum numbers, and set 2, and so on and so forth. And I want you to pause the video and take a close look and tell me which of the following quantum numbers cannot exist, and be prepared to explain your reasoning. Keep in mind there may be more than one possible correct answer. In other words, there may be more than one set of numbers that cannot exist. Let's go through each set and tell whether or not they exist or don't exist. Now let's take a look at the first set. Now in the first energy level, there's only one possible subshell, and that's an S subshell. And S subshells are only designated with the 0. So this is not possible. You cannot have an L value of -1. In fact, L values can only be 0, +1, +2, or +3. So there's 2 reasons that this number can't exist. First of all, L's can't be negative. And second of all, because we're in the first energy level, you can only have 0 for an L value. Now let's take a look at the second set of quantum numbers. So we're in the second energy level now, and the possible values for L in the second energy level are 0 or 1. So this is good. Now, since we're in the subshell 1, that means my possible ML values are plus or minus 1 and 0. So this plus 1 works out as well. And inside, the spin number for that orbital can either be plus or minus 1/2. And so if you see either a plus or minus 1/2 in this last column, then it's probably good. So in all of these sets, in fact, this is a good value or an acceptable value for the spin number. So this one's okay. Set number 3, third energy level, you can have a 0, 1, or 2. And since this L value is 1, then it checks out, it's okay. Now, move on to the M value, or the M sub L value. Since the L value is 1, we are limited to plus or minus 1 or 0. And this ML value is -3. So this is what's wrong with this set. This is not possible. You cannot have a -3 if your L value is 1. And so that disqualifies set number 3 as being a possibility. So that means that this cannot exist. Now let's take a look at set 4. Fourth energy level, so that means we can have a possible L value of 0, 1, 2, or 3. This one checks out. Since we've limited ourselves to L value 1, then my possible ML values are plus or minus 1 or 0. This one checks out. And finally, plus 1/2 is an acceptable number for the spin number. So of the 4 sets, set number 1 is impossible and set number 3 is impossible. And be prepared to explain why that this one cannot exist, or this one cannot exist in set 3 if a question like this comes up on an upcoming quiz or test. Well, that takes care of this video lesson. Thanks for watching.